Just want to let you know. All right, so we're on 2B.3, exponential and log forms of equation. The main purpose here is to realize that everything is a pattern and for us to recognize those patterns and use those patterns going forward. This is a build on to 2B.2, meaning that in 2B.2, we talked about that the inverse of an exponential is a log model, right? A log function. Therefore, the inverse of a log is exponential. So here we go. So when we're doing this, when you're dealing with logs, you want to think about them in terms of an exponent. This to what power equals this, okay? That's because they are closely related and they tie together, all right? So starting off is the definition of a log. The definition of log is if b and n are positive numbers, so b and n, so the base of your log and your argument are positive numbers, then if and only if, then therefore the log base b, right pen, and then only if your base of your log is the base of your exponential. The argument of your log is the solution to your exponential. And the solution to your log is the power of your exponential. Okay? So the base stays the base. The argument becomes the solution. The solution becomes the power. Okay? Do we see that? Because they're interchangeable, and then all of that works vice versa. For your exponential, the base stays the base. The power becomes the solution. The solution becomes your argument. Essentially, your independent variables and your dependent variables do what? Switch. They switch properties because they are inverses of each other. Does that make sense? Okay. At the top of your paper, you should have a blank white space. At that blank white space, we're going to see a numerical example. We're going to write in a numerical example. Does that make sense? Okay. For that numerical examples, you can write the words around it or not write the words around it. Is 100% up to you. Got it? So here is what you're writing. So we have log base 3 of 81 equals x. This is the original log. Okay. When we say we should think of a log as an exponential, we're saying 3 to what power equals 81. The base stayed the base. The solution became the power. The argument became the solution. So now could you answer that? 3 to what power equals 81? Anyone knows? Fourth power. There you go. So x would equal 4. And you just solve the log without a calculator. Does that make sense? Do we see the connection? Yay, nay, maybe so? All right, so to drive in that rule, we're going to practice converting from log to exponential, okay? They're already completed and solved, but we're showing how they make true statements. Does that make sense? Yay? Nay? All right, I'm going to move on. Can I move on? No? Okay. Yes. It's interchangeable. It goes back and forth. Yep. Okay. So to show that this is true, so when you are solving a log, you're taking the exponent, you're raising it to the exponent of the base. So my base here is 2. So this is 2 raised to log base 2 of 8. What I do to one side, I'm going to do to the other side. What the rule, the definition is telling you, if you remember the rule, then you don't have to do this every single time because the pattern already exists. If you don't remember the rule, then you just use your idea, your knowledge of inverse operations. Okay. So when I raise, what ends up happening is the base of the exponent, the base of the log are the same. So it sets my argument free. And I'm left with 2 to the third. Does 8 equal 2 to the third? It does. So, oh my gosh, it must be true. The definition is true. That's crazy. Okay. Does it change it? Yes. Nope, it does not. It does not matter which side you write which one. Okay. So again, when we are looking here at log base 2, 1/4 equals -2, we're saying that you're looking at the base of the log. And what's the base of my log? 2, right? And then your solution becomes your power, and your argument becomes your solution. Yay, nay? So if you have a hard time recognizing the pattern, then your fallback is to just use inverse operations, which is raising this to the power. So 2 to the -2 equals 1/4, which is true. When you have a negative power from Algebra 1, part of your exponent rules is if I have a negative power, I'm going to do the same power. So 2 squared is 4, but because it's negative, that means it belongs in the denominator, which is why it is 1/4. Do you guys remember your negative power rules from Algebra 1? Okay, if you don't, then you may want to make a note to yourself that if you have n to a negative p, it equals 1/n. So any number to a negative power is going to be 1/n. Got it? And vice versa. If you want to take a number out of fraction, then you just need to put it to a negative power. Okay? All right, let's keep going. Which method, following the pattern or taking the exponent, works best for you? It's totally up to you. If you forget, so I'm going to raise it to the 2, raise it to the 2, cancels out. So I'm left with 1 equals 2 to the 0. Is that a true statement? Yes, because anything to the 0 power is 1. If you're a person who sees the pattern, you're like, okay, my base is 3. My solution is 4. My argument is 81. So 3 to the 4th equals 81, which we already had confirmed because we wrote it at the top of our paper, correct? True statement. Okay, so again here, when we see we have log 16 of 2 equals 1/4, our base is 16. Our solution is 1/4, which becomes our power. And our argument is 2. So 16 to the 1/4 equals 2. You're probably like, how does that work? This is what we call a rational power. When you have a rational power, that means you're taking the root of that number. Okay, so 16 to the 1/4 means that I am taking the 4th root of 16. So what number times itself 4 times makes 16? It's 2. 2 times 1 is 2. 2 times 2 is 4. 2 times 2 is 4. 2 times 2 times 2 is 8. 2 times 2 times 2 times 2 was it 4? It's 16. We're going to pretend that was 4 of them. Okay, it's 16. So therefore, that's why the solution is 2. The 4th root of 16 is 2. So anytime you have a rational power, that means you're taking the root. You're saying what number. Okay, that should have been an exponent rule as well. Log base 8 of 2 equals 1/3. I'm like, oh man, I forgot how to do this. Well, if I forget how to do this, I'm taking the base of the log and I'm raising both sides to the base of the log. When I say I'm raising, that means that this is now an exponent. It's now a power. That's going to cancel this out. And I'm left with 2 equals 8 to the 1/3. Again, I have a rational power. What does that rational power mean? Root. Means I'm taking the root. So I'm asking myself, what is the cube root of 8? what number times itself 3 times equals 8? And that answer would be 2. 2 times 2 times 2 is 8. Okay? Questions, comments, concerns? All right, the real test is if you understand this, then you can undo. So if you understand, then you can undo. So I'm going to give you about 5 minutes. During this 5 minutes, you're going to undo these exponentials and turn them back into logs. So if you understood what we did on the first half, then on the bottom half, you're undoing it. Okay? So what is the log representation of what we have? Go. So here we have the rule. So remember, when you're going backwards, it's going to be, the base is still going to be the base. So the base of the exponent is the base of the log. But your input and your output are what's changing, are switching places. So the power becomes the solution becomes the argument, right? So for 7, that's what you should have had. For 8, what should we have had? Log base 2 of 1/2 equals -1. On 9, yes, your base is 32. Log base of 32 of 2 equals 1/5. Remember, this means that you're taking the root. So what number times itself 5 times equals 32, which would be 2. 8 squared equals 64 becomes log base 8 of 64 equals 2. 11, we got log base 5 of 1 equals 0. And 12, you should have gotten log base 6 of 6 equals 1. Okay? This is always going to be true. If your argument is 1, no matter what for a log, no matter what the log is, if your argument is 1, it's going to always be 0. Okay? On here, if the base and the argument are the same, or these two are the same, then it's going to always be 1. That's called our identity for logs. All right. So we see the pattern, we understand the definition, right? Yes? Okay. The beauty of this is how we solve. So this is how you solve log functions without a calculator, is by understanding that pattern. So here we have log base 5 of 25 equals something. We currently do not know what, okay? So what you're asking yourself is 5 to what power equals 25? Okay? That's what you're asking yourself in your head every single time, right? And can I answer it now? Yeah. 5 to what power equals 25? 5 to what power equals 25? And the answer is x equals 2. So when you see a log and you're solving the log, you should think of it as a question. So let's try 14. So 14, we have log base 4 of 64 equals x. So I'm asking myself, 4 to what power equals 64? So 4 to what power equals 64? And that's going to tell me my x. Anyone? Everyone? 3. 4 times 4 is 16. 16 times 4 is 64. So 4 to the third power equals 64. And we did it without a calculator. I don't know why you did. All right, let's try this one. So again, Imagine that this is unknown, so we're going to put x. So you're asking yourself 4 to what power equals negative 16? And your cell should say, red flag, red flag, red flag. Why is it a red flag? It's negative. You have a negative log, and our first definition is that your base and your argument have to be positive, right? And then you also have a negative output for an exponent. And if you did your homework, what did it tell you? It was undefined. You did your homework on the last problem, you should have gotten undefined. All right, log base 10 to the 3. I want to bring up, when you have log base 10, you never really actually would see log base 10, but for the sake of learning, that's why it's here. Normally, this would just say log 10 to the third. When log is by itself, it's an implied that it is a 10. Does that make sense? When log is by itself, it's implied that there is a 10 there. So when you see this, you will never ever see this outside of our notes. Outside of our notes, you would just see log 10 to the third. Does that make sense? Okay. All right. The reason why, and this is called our common log, because this is what's typically used. But anyways, we're asking ourselves 10 to what power equals 10 to the third? What would make these true? What would make these look the same, guys? 3. X equals 3. Okay, the next 3 are the ones that we have to work a little bit more for to get to the answer. Okay, and that's because we're going to start off without having the same base or an obvious answer like this before. So here we have log base 3 of 1/3. If I have log base 3 of 1/3, I'm asking myself 3 to what power equals 1/3? Okay. Okay. Before I get started, I want to change this into a non-fraction. To change this into a non-fraction, I have to remember my exponent rule, which means that I'm actually going to be working 3 to the x equals 3 to the negative 1. So what does x have to be for these to be the same? X simply has to be negative 1. When the bases are the same, all you're doing is focusing on is the powers. So we end up with x equals negative 1. Okay. How do you feel about taking a fraction and turning it into non-fraction? All right. Let's keep her going. Next is what to do when you're like, I don't know that. It's okay. We're going to talk about it. I have log base 9 of 3. So you're asking yourself 9 to what power equals 3? 9 to what power equals 3? And you're like, oh, that's a tough one. Yes, when it becomes a tough one, you're actually going to ask yourself, how can I change 9 to a base of 3? How can I change 9 so that it has a base of 3? Or how can I change both of them so they have the same base? Well, 9 is the same thing as what? There you go, 3 to the second. So I can rewrite 9 as 3 to the second x equals 3. Now my bases are the same, so all I have to do is worry about the power. And if there's no power there, who's there? What number is there if there's nothing there? 1, Casper the friendly one. When there's no number that is being multiplied, that's Casper, right? Casper the friendly one appears. So now you're just solving basic algebra. 2x equals 1. What is x? X equals 1/2. Which makes sense because the square root of 9 is 30. And 1/2 means I'm taking the square root. Okay? 19 is going to combine 17 and 18 strategies together into one problem. If you can do 19, you can do all things. So let's talk about 19. All is a little extreme, but you know what I mean. All right, so this is asking me 16 to what power equals 1/2. So we have 16 to what power equals 1/2. So the first thing I'm going to do is change my 1/2 into a non-fraction. To change 1/2 into a non-fraction, it's going to become 2 to the negative 1. Agreed? The next thing I'm going to do is figure out how can 16 and 2 have the same base? How can I write 16 in terms of 2? How can I write 16 in terms of 2? 2 to the 4th. So 16 is going to become 2 to the 4th, which equals 2 to the negative 1. Now that my bases are the same, to solve, I just have to focus on the powers. So we have 4x equals negative 1. What does x equal? Negative 1. And you did it all without a calculator. You're the human calculator. Okay, how we do? Doable? Okay, so what you're going to do for the next 10 minutes is you're going to work on your exit ticket. So your exit ticket is a combined review of 2B.1, 2B.2, and 2B.3. Okay? It goes in your notebook. This is the last page for our notebook check, by the way. So it goes in your notebook. With a partner, you're going to work through each problem, and then you're going to check with other partners, other group sets, to see if you and your partner did it correct. Okay? So it's a cumulative of 2B.1, 2B.2, and 2B.3. Got it? And I'm going to give you 10 minutes to work. Capiche? All right. If you finish, as you guys finish, don't be mad. Don't hit me. There's a series of papers that I need you to grab. So on my table, the round table right there, as you finish, you're going to grab one of each paper that is laid out there. That is every single paper that I need to give you until the end of the semester. Okay? All right.